Very warm welcome. Okay, let me get started with a broad introduction over the goal, why actually we need epitaxial graphene quantum metrology. So since March 2019, we officially entered a new era of measurement and metrology. It's a special time because the redefinition of SI units come into force by setting the exact numerical values for the selected physical fundamental constants. So this is a special time, and I'm so happy that I had the privilege to work in this period of time in this area. So in the field of electrical quantum metrology, the unit of electrical resistance can be redefined using von Klitzen constant. This has been so far achieved in conventional semiconductors like gallium arsenide, but it's also possible in graphene. The main advantage of graphene is that it enables us to have the quantum Hall effect measurements at pretty high temperatures and lower magnetic fields. So this has motivated metrology institutes to have the graphene-based quantum resistor metrology. So for a robust quantum resistor metrology, we need high-quality graphene. The high quality here refers to meeting the following requirements. So we need to have a processes to get large area single layer graphene without any add layer or bilayer. We need to tune the charge carrier density, and it should be stable over time. So epitaxial graphene already comes with several striking advantages. We can directly grow the graphene on a substrate, so we do not need to transfer it on another substrate. And it's already doped by the substrate. But there are also several fundamental challenges. The challenges like defects, like step bunching, or the thickness control, like the bilayer inclusion, as well as a so-called anisotropy transport in epitaxial graphene, which highly degrades the metrology application of this material. But today I'm going to show you how we can solve these problems. We can get large area, pure single layer graphene without any bilayer inclusion, which shows for the first time isotropic transport properties. You will hear about this and more during my talk as optimization of epitaxial graphene growth on silicon carbide for quantum metrology. So here's a rough outline. I had the privilege to work in several different areas. I mainly focus on graphene growth, on big family of epitaxial graphene. My study also covers electron transport properties, mainly resonance anisotropy in epitaxial graphene, as well as magnetic transport, or using the graphene as a platform for growing other 2D materials, or our new understanding about the influence of substrate on top layer graphene. And today I'm going to focus on these three areas of my talk. So many of you are already familiar with principle of growing graphene epitaxially. The main process is very simple. If you heat the silicon carbide at high temperatures, like up to 1500 Celsius, you get a layer which is partially covalently bonded to the substrate. This layer looks very similar to graphene, but does not show electronic properties like graphene, so it's electronically dead. If you proceed the annealing at high temperatures, then you get a second layer. And the first layer turns to monolayer graphene. That's how we get epitaxial graphene. So again, as you notice, when we are talking about epitaxial graphene, we are not talking about a single layer graphene, but it's also a like layer which is partially bonded in substrate. You can even go further, anneal the sample at high temperature, then you get epitaxial bilayer graphene. But epitaxial graphene has much bigger family. It's been shown if you anneal buffer layer or epitaxial monolayer graphene in a hydrogen, for instance, environment, you can decouple the buffer layer from the substrate. So that's how you get a quasi-freestanding monolayer graphene. That's the same scenario for the quasi-freestanding bilayer graphene. At the PTB, we kind of modified the standard sublimation growth of epitaxial graphene by adding some polymer to the samples during the preparation. This method is called Polymath. It's a sublimation growth. To prepare the samples, we first dig the samples into a mixture of isopropanol and acetone and polymer, and introduce the ultrasonic bath for a while, and then we take it out and wash it off with isopropanol, and this leads to nano-sized polymath everywhere on the sample. The process looks very simple, but it's very efficient. And as I said, it leads to nano-sized polymath everywhere on the samples, which act as a carbon source and support the process later. So the samples then are ready to be loaded into the oven, as you can see here on the left side or right side. Yeah. And the process is the main process is performed at in Argo ambient, different temperature and time windows. So during the growth, the polymer cracks, and it leads to nucleation of the carbons on the terraces as well as steps area, and leads to rapid formation of the buffer layer, which highly helps to avoiding step bunching during the process. However, the process is pretty complex and yet requires a lot of optimization. Here you can see the two very famous polytypes that are mainly used, 4H and 6H SiC. The difference between these two polytypes are the number of layers. So we have, in 4H, we have 4 layers stacking in the unit cell, and 6H has 6 layers. These layers could be either hexagonal or cubic. So as you can see here, the main point is when we cross the hexagonal layers, the crystal rotates with 6 degrees, as you can see, or follow this through these cyan color tracks. So here you can see how the surface of the sample looks like. So we don't have a flat surface, but we have steps and terraces. This arises from the miscut angle. So we have a miscut angle. We cut this wafers samples with a slightly miscut angle toward a special crystal direction. That leads to formation of these steps and terraces. So in case of these terraces, this miscut leads to formation of different terraces. For instance, in the case of 6H, we have 3 types of terrace terminations, named as S3, S2, and S1, as well as 3 star, S2 star, and S1 star. So the Sn and Sn star, like S3 and S3 star, are the same, but the crystal is rotated 60 degrees with respect to each other. So the surface energy of these terminations are different. So now we can imagine that during the growth, they drive the surface diffusion differently, as you can see from the arrows on top of each termination. So the S1 is the first which removes or dissociates, and S2 is the last one, and S3 has the middle state. But it's not the only step retraction model in the literature. So if you see in the literature, you can see there is a kind of discrepancy as has been shown in the red arrows here, which I will explain later by introducing a so-called JCH, or a joint cubic hexagonal model to clarify this discrepancy. But no matter which step retraction model, during the growth, the steps move together or bunch together and form higher steps. This leads to 2 problems. So we have this usually is accompanied by bilayer inclusion at the step areas, which gives rise to problematic of resistance anisotropy due to this due to increase of the resistance at the step areas. Well, here you can see the top view of the wafer that we are using. So the samples with this different size are cut from the wafer. You can see that we have a pretty complex material system, depending on which miscut angle, which crystal plane, or which surface plane that we are using, we can get different qualities. For instance, on the C side, you cannot get a buffer layer, which is the case on the silicon side. So the growth is pretty complex. In this study, I'm going to show you the result on 4H and 6H SiC with a miscut angle towards this crystal plane direction. So with this little introduction, I'm coming to the second part of my talk, which I'm going to show you the advanced control epitaxial graphene growth to get a pure monolayer graphene as well as freestanding graphene layers. So let me begin with the buffer layer growth. So buffer layer growth is very, very important because it defines the quality of the freestanding samples, and as well as epitaxial graphene, right? So technically, we have two main challenges regarding buffer layer growth. One of them is low coverage, which is happening mainly due to the low temperature process compared to the graphene process, and leads to lower surface diffusion. Or the other one is the excessive coverage, which happens if you increase the temperature at high temperature, then you get a graphene at the step areas. So these two problems, these two fundamental problems, you can see better in these three exemplary samples. So the samples processed with the same time, but at different temperatures, as you can see. From the AFM topography of the sample, you can see different step bunching, or the morphology of the samples are different. So this shows the different step bunching states. The point is, however, considering the AFM phase images of these samples, so you can see that we have a kind of phase contrast on all samples, which arises from the material contrast. So we have a mixture of silicon carbide and buffer layer. So now we can notice, even if at 1500 Celsius we have a rift or a gap between the terraces, which is uncovered, right? So we can imagine now, if you intercalate the sample, your graphene won't be connected. So you have always a rift between. That highly degrades your making devices out of this kind of graphene. So because you are technically restricted to make your device only on one terrace, right? So this is a very challenging problem, and although the history of epitaxial graphene goes a long time ago, so far has not a homogeneous buffer layer has been reported in the literature. But this problem can be solved by applying the optimization. On the right side, you can see the larger scale AFM topography of the sample as well as phase image here. On the left side, you can see a closer look. So you can see that the steps and terraces are very homogeneous, indicating very uniform growth. It can be more clear when you notice the step height profile. So we have kind of steps of 0.25 and 0.5 nanometer. I'm sorry for the pointer, it kind of doesn't really work. Good. So the step bunching has been very highly suppressed. So we have very small steps. We don't see any defects, as well as, I mean, you can see also in the Raman spectroscopy of the buffer layer spectra here, mapped here, you can see very homogeneous buffer layer. Good. We can test the quality of the buffer layer by applying hydrogen intercalation. So here you see the results. The lead pattern here indicates or demonstrates the successful intercalation. And here on top, you can see the larger scale scanning tunneling microscopy image of the sample. So you can see that the graphene smoothly goes from one terrace to the next with a step of 0.25 nanometer in between. A closer look at the atomic scale of this sample shows that a high quality of graphene crystal. On the right side, you can see a much better two graphene bridging over two typical steps of producing on this sample, so 0.25 and 0.5 nanometer. So what is showing here, we have been able to successfully grow high quality buffer layer, which is intercalated and shows that very smoothly graphene can be fabricated on, or freestyle graphene can be fabricated on the on epitaxial on silicon carbide. So now let's have a look on the epitaxial graphene samples. So here you see two exemplary samples on 6H and 4H silicon carbide. From the morphology of the samples, from the atomic topography of the samples, you can see that the steps are, again, very homogeneous and uniform on both substrate, which again indicates uniform graphene fabrication. However, if you look into the AFM profile of these two samples made from these two white lines, you can see on the 6H samples, the steps and terraces are arranged in a sequential manner of 0.25 and 0.5 nanometer, which is not the case in 4H. So now we can learn a little bit more about the difference between the polytypes, or the influence of the polytypes. So from the histogram made from different scanning all over the samples, you can see that in case of 6H sample, we have like 90% of the steps and terraces with a height of 0.25 or 0.5 nanometer, which in the case of 4H, we have like less than 70% below 0.75 nanometer. So we can now successfully suppress the step bunching. We can get very homogeneous surfaces on both polytypes. So just let me add that these are all so far exemplary samples. I mean, we can get reproducible fabrication of such quality samples. So, getting high quality graphene entails multiple optimization. So here I'm going to show you one of the important growth parameters, the argon gas flow, which so far has been less regarded or neglected. So here you can see 3 samples processed with the same condition, only the gas flow is different. So here we have 0 SCCM, in the middle we have 100 SCCM, and the right we have 1000 SCCM gas flow. From looking the topography of the sample, we can see a difference. So totally, so for instance, the sample process 1000 SCCM shows really a giant step bunching or high step bunching. This can be more clear when you look into the AFM height profile of the samples, of these 3 samples. So in case of 0 and 100 SCCM samples, if you notice or if you take a look on the lead pattern of these 2 samples, we can confirm that we have a buffer layer formation, which is not the case when we have 1000 SCCM argon gas flow. So here, the argon gas flow led to etching the surface. It's even more interesting when we notice the topography, the AFM phase images of the samples. So in case of 100 SCCM and 0 SCCM, we can see that when we have like a gentle gas flow, like 100 SCCM, we get some kind of canyon-like defects, which is not in case of 0 SCCM. So in this case, we have, of 0 SCCM, we have a kind of slightly wrap between the steps, as you can see in this image. So what does this mean? This means that we can clearly see that the argon gas flow can cause some defects or even etch the surface. So we know that if something can destroy, right? If we can control it in a way, we can use it as a growth parameter. So that's why that was one of the optimization that I did during this work. Before proceeding, let me show you some new results. So these guys, like a couple of weeks ago, I think, or like end of August, they published a work. They repeated the same experiment, but in a CVD process sample. So they also could confirm the same influence of the argon gas flow during the process. So let me wrap it up. So far, I have shown you that we can have high-quality graphene samples, so large area, bilayer-free graphene samples. we can also successfully grow buffer layer graphene-free samples and then intercalate it to get freestanding samples. I showed you that the argon gas flow has a big influence in the growth process, and it can be used as a parameter as well. And so during this work, I've grown more than 1,200, 300 samples. So we have really reproducible samples process. So the next I'm going to show you or talk about more the electronic properties of the samples, the resistance non-entropy in epitaxial graphene.